Swayam Prabha. Digital India. Educated India.
So, welcome back to lectures on advanced calculus for engineers, and this is lecture number 25, and here we will discuss on linear differential equations. So, in particular we will go through the first order linear differential equation in this lecture, and then there are some equations which are reducible to linear differential equations. So, those equations will also be considered, and of course their solution techniques. So, just to recall what was the integrating factor which was discussed in the previous lecture. If we multiply an equation which is not exact by some function, and then the equation becomes exact, we call such a function Ixy as integrating factor. So, there were two formulas were derived. One was that if this my minus nx divided by n is a function of x only, and let us call this term as fx, in that case this e power fx dx becomes the integrating factor of m dx plus n dy equation. There was another formula that if 1 over nx minus my is a function of y only, in that case, so let us call this term as gy. In that case the integrating factor will be e power integral gy dy. So, there were several other forms, several other ways also to evaluate or to identify this function integrating factor. But now we will just focus on these two for the linearity of the equation or for the linear equation. So, a first order differential equation is called linear, we have discussed before also. So, this is the general form that dy over dx plus pxy is equal to qx. So, this is the general form of a first order linear differential equation, where this px qx are the function of x. This we can rewrite this equation in this differential form. So, we have dy, we will just multiply with the differential dx to this equation. That means, we have dy plus we have p x into y and then dx, and then the right hand side also we have qx and dx. So, in this case if we compare with m dx plus n dy equation, then what we will see that m dx, so only this part we are talking about, the right side is not 0 here. So, that is qx dx in this case. So, if we compare this, then m is like py and n is 1 in this case. And then we observe that this 1 over n my minus this nx is equal to, so 1 over this n was 1 and then del m over del y. So, this is p and minus del n over del x will be 0. So, we have just this p x. So, 1 over n my minus n x is p x. So, function of x only, and in that case we know that the integrating factor will be e power p x. So, if we multiply the whole equation by this e power integral p x, the left hand side will become a total differential of some function, and then after integration this equation can be solved. So, that is the idea how we solve the linear equation. So, this was a given differential equation, the linear differential equation, and if we multiply by this integrating factor to all these terms here on the left hand side and on the right hand side, then what we should get now, because this has to be a total differential as per the definition of the integrating factor, and which is indeed the case. So, this is the total differential of e power integral p dx y. So, if we just expand this differential, so we need to partially differentiate with respect to x this one, that means e power p dx, and then the derivative of this integral p dx, which will be p, and then we have y as it is, and we have dx plus the partial differentiation of this term here with respect to y, which will be e p dx, and then we have dy. So, this is the total differential which is exactly given there, e power p dx dy plus py e power p dx and dx. So, therefore, we have written this d of e power integral p dx into y. The right hand side we have qx e power p dx. So, now if we integrate this equation, what will happen? After integrating, we will get e power p dx into y, and the right hand side we have again this integral q e power p dx plus a constant term. So, this is the solution of the given linear differential equation, which we can remember in this form, that once we have the integrating factor we can get easily from this e power p dx. So, our equation, the given equation will be dy over dx plus px y is equal to qx. So, given this linear differential equation, we will find the integrating factor e power p dx, and then once we have this integrating factor, we will write the solution directly, that y into this integrating factor is equal to the right hand side q, which will be also multiplied by integrating factor, and then we have to integrate that right hand side plus a constant term. So, this is the solution of a linear differential equation. We will find the integrating factor and then substitute in this formula. We will integrate this and write down y in terms of x. Well, now sometimes a differential equation cannot be written in the form dy dx plus p y is equal to qx, which is linear in y. It is linear in y. We have dy over dx, then we have y term, and we have that function of x. But it can also be written like dx over dy p1 y x into q1 y. So, we have to see whether equation is linear in x or it is linear in y. So, if it is linear in x, naturally we have to solve for x as we have solved for y. So, in this case the integrating factor will be e power p1 dy, because this is p1 now here. So, p1 dy, and then the solution will be x into integrating factor, and the right hand side we have this q1 into the integrating factor. We have to integrate now with respect to y plus a constant. So, in that case our solution will be given by this formula. Let us go through some examples. So, here we have 1 plus x square dy dx 2xy minus 4x square. So, this is clearly linear in y, and we can write down in that standard form. So, dy over dx we divide by 1 plus x square. So, we have 2x over 1 plus x square y is equal to 4x square and divided by 1 plus x square, which is linear in y. Now, the integrating factor. So, we have exponential integral of this p dx. So, p dx here is 2x over 1 plus x square dx, and this integrating factor, because here the derivative of this 1 plus x square is given as 2x in the numerator. So, we have simply e power 1 plus ln 1 plus x square, which is 1 plus x square. So, 1 plus x square is the integrating factor for this linear equation, and then we have that formula that y into integrating factor is equal to q into integrating factor dx plus a constant. So, y into this integrating factor, which is 1 plus x square, then the right hand side we have the integral, and q in this case is 4 x square plus 1 plus x square, and integrating factor is 1 plus x square. So, this term will get cancelled, we will have only 4 x square dx plus c, which can be integrated to give here 4 by 3 x 3 plus c, y into 1 plus x square is equal to 4 by 3 x 3 plus c. So, this is the solution of the given linear differential equation. Well, another example where it is given x plus 2 y cube dy over dx is equal to y. So, certainly because we can see here y cube, this equation is not linear in y, but we have to just see whether it is linear in x. So, if we write as this equation, so y into dx over dy is equal to x plus 2 y cube, or dx by dy we can divide by y. So, we have minus x over y is equal to 2 y square. So, this equation is a linear equation in x, this is linear in x. So, we can use the formula which we have for the linear equation in x. So, integrating factor, first we have to use this one here in the integral. So, e power minus 1 over y, and then we have dy there, is equal to e power minus ln y, and that is equal to 1 over y. So, here the solution will be x into 1 over y is equal to 2 y square into 1 over y dy plus a constant, because x into this integrating factor, the right hand side factor is 2 y square into the integrating factor 1 over y dy plus c. So, here then we get 2 y dy, which can be integrated as to give y square. So, we have x over y is equal to y square plus c, that is the solution of this linear equation. So, equation reducible to linear form. So, there are certain equations which can be reduced after some substitution to linear form. So, what are those equations? So, an equation of this form f prime dy over dx plus this p f y is equal to this q x. If we have an equation in this form, here the derivative of this term is sitting, that is important. So, once we have this form of an equation, then we can convert this equation to an equation which is linear in x, for linear in y in this case. So, if we substitute here this f y is equal to v, this function f y whose derivative is sitting here in front, if we set this f y, this function as v, then what will happen? So, here this f prime y dy dx is equal to dv over dx, and this f prime dy over dx, which is the first term of the equation, will reduce to dv over dx, and here also we will get v. So, the equation will become linear in v in that case. So, the equation reduces to dv over dx. So, instead of y, now we have this v variable. So, dv over dx, then plus pv, and the right hand side is just qx, is not changed, only the y variable is changed. So, this the whole function of y is set to v, and then we have the equation in v only. So, as a special case, we this equation is known as Bernoulli equation, an equation of the form that dy over dx py and is equal to q y power n. So, in the right hand side we have here y power n. So, this is not a linear equation, but it can be reduced to a linear equation. So, here also p and q, these are the constants or function of x, and n is a constant except 0 and 1, and this equation is called Bernoulli differential equation. How to solve this equation? So, we can rewrite this equation in this form: 1 over y power n dy over dx plus p over y power n minus 1 is equal to q. So, if we divide this whole equation by y power n, then we got this 1 over y power n dy dx is equal to p divided by y power n minus 1, and then right hand side we have this q. So, if we substitute now 1 over y power n minus 1 as v, if we substitute this, then what we will get here, we differentiate this. So, what we will get, this is y power 1 minus n, and then after differentiation we will have this. So, derivative of this will be 1 minus n and y power we have minus 1. So, this minus n and then dy over dx. Yeah, so, this is precisely the derivative here, and then the right hand side will be dv over dx. So, this one now can be substituted in this equation. So, 1 over y power n dy over dx is exactly dv over dx and divided by this 1 minus n plus this p v is equal to q. So, this 1 minus n can also be multiplied, then we have dv over dx p into 1 minus n into v is equal to q 1 minus n, which is a linear equation in v. This is a linear equation in v. P and q are functions of x. Well, so let us consider few examples of such equations which can be reduced to a linear equation. So, here this equation, if we can rewrite this like 2xy dy over dx. So, this differential we are dividing everywhere, then we have x square minus 2x and plus 2y square. So, here we see this 2xy term is there. So, if we just divide by x also, we will get here 2y, and then this 2y square divided by x. So, we keep it, and the right hand side then everything of x. So, 2x minus x square and divide by x. Why we have done so? Because if we now set this y square to some v, in that case this 2y dy over dx will become dv over dx, and here also we will get v, and the equation will become linear in v. So, if we substitute this y square is equal to v, then 2y dy over dx will be dv over dx. So, we have here dv over dx plus 2 over x into v, into this v, and this is a linear equation in x, then an integrating factor we can just get. So, e power 2 over x dx in integral. So, that is x square, because this is ln x 2 ln x. So, here e power 2 ln x, and this is nothing but ln x square. So, we will get just x square as the integrating factor, and once we have the integrating factor, we can write down the solution. V into x square is equal to this integral 2 minus x square, this integrating factor dx plus c, and this can be integrated to give, now v we can substitute as y square. So, it is y square x square is equal to here 2x square. So, we will get 2x cube by 3 minus this x cube. So, we will get minus x 4 divided by 4, and then we have a constant term. So, this is the solution of the given differential equation, which was not linear, but after this substitution y square is equal to v, this became a linear equation whose solution is given here now. So, another equation dy over dx minus y 10x, and the right hand side we have minus y square sec x. So, here if we divide by y square, what will happen? So, we have 1 over y square dy dx minus 1 over y 10x is equal to minus sec x. So, here also if we take this 1 over y as v, then its derivative will be 1 over y square with minus sign, and dy over dx, this will be dv over dx. So, now we can substitute in this equation, and what we get? We get dv over dx, and we multiply at the end with minus sign. So, here 1 over y will be dv over dx, well, 1 over y is just dv, v. So, here we have v, then we have tan x and equal to, because we have multiplied by minus sign, here we have this secant x. So, the integrating factor now for this linear equation, which is linear in v, we can get e power integral 10x dx. So, integral 10x is sec square ln sec x, because this 10x is nothing but sin x over cos x, this integral, and this the derivative of this cos x is sitting here in the numerator as sin x. So, then this integral will be minus ln and this cos x, which with minus sign here we can write down as ln sec x. So, here this sec x is the integrating factor for this equation, which is linear in V. And now we know the formula for solving that linear equation, that V into this integrating factor is equal to sec x into again sec x dx plus a constant. So, we have here this sec square x, and that is 10 x plus c, and we have V sec x here. So, y inverse, because V was 1 over y. So, we have y inverse sec x is equal to 10 x plus c, that is the solution of the given differential equation. So, here also the idea was same, because we do see that the derivative of this is sitting here, then we can make a substitution and then the equation will become a linear equation. So, this is the last problem. So, here we have x 4 e power x minus 2 y square x dx, and then here we have 2 x square y dy. 2 x square y dy is equal to 0. There is an initial condition given here, y at 1 is given as 1. So, this is 2 x square dy over dx, and this minus 2 y square x, the right hand side is everything of x, this minus x 4 e power x. And in this case we have a similar observation that we can first of all divide by this x square. So, after dividing this x square, we have 2 y dy dx minus this 2 y square over x, and the right hand side will be just minus x square e power x. So, in this case also, if we substitute this y square as v, then this 2 y dy over dx will become 2 dv over dx, and then here the equation will become linear in V. So, we have dv over dx and minus 2 v over x is equal to minus x square e power x. This is linear in V. So, we can find out this integrating factor. So, integrating factor will be e power minus 2 over x dx, which is just e power minus this ln x. So, the integral will be minus ln x 2 times ln x, and this is e ln and this x minus 2. So, this is 1 over x square. So, our integrating factor here is 1 over x square. So, this 1 over x square, then our solution will be v into this integrating factor. The right hand side is minus x square and then e power x, and then which will be multiplied by 1 over x square. So, we have e power minus x there. So, integral minus e power plus x plus this constant, and then y we can substitute as y square. So, it will be y square is equal to this x square e power x and plus c x square. So, this is the general solution of the given differential equation, but we have a condition here that y 1 is given as 1. So, we will substitute here this y 1 as 1. So, here 1 is equal to minus e and plus this c. So, c is 1 plus this e, that is the constant. C is 1 plus e using the initial condition given in the problem. So, c is 1 plus e, then we can substitute this c here. So, y square is equal to minus x square e power x, and then this c is 1 plus e x square. So, we have the particular solution now of the problem, which is free from the arbitrary constant, because we have used this initial condition to evaluate that arbitrary constant here in this problem. Well, just to conclude, so in this lecture we focused only on linear differential equation of order 1, which is given here in general form dy over dx is equal to plus p x y is equal to q x. And what we observed that there was another type of differential equations which can be converted to linear differential equation, and in general the type of those equations was that if f y is sitting here, then its derivative is f prime y, and then just by a substitution that f y is equal to this v, it converts to the linear differential equation. And once we have linear differential equation, we can find out the integrating factor, which is e power p x dx. And once we have integrating factor, the formula was that y into this integrating factor is equal to the right hand side q x into integrating factor and plus a constant. So, this will be the solution of the linear differential equation, which was discussed through various examples. Well, here we have the references which I used for preparing this lecture, and with this I thank you very much for your attention.